I am going to go to where we left out this morning. All right. And before I do that, I would like to show you a little demo with continuing with what Tim was talking about this morning. With I have here a little example demo of a comparison between 2D and 3D problems. So I generate, this is an example I always give in class, and I was watching the sizes of the problems grow from year to year. I could do now on a laptop with a few seconds, about 125,000 unknowns with a direct method. So this is a 3D grid. There's two grids. One is 2D and the other one is 3D, but they end up with it's exactly the same number of unknowns. So 350 by 350 by 1, that's 2D grid, or 50 by 50 by 49, it's 3D. So if you make the calculation, you will find that the number of unknowns is 122,500. So I'm solving this problem through the direct method, just backslash MATLAB. Okay. And you'll see it's the same size. The number of non-zero elements is not very, very different. It's on average 7 for the per row for 3D and 5 for the 2D problem. So it's, it's a small difference, but it doesn't account for the difference in time that you'll see. So let's run it. Where am I here? No. Okay, I'm going to go back to Spark here and then demo 2D versus 3D. Okay, so here you go. So this is the size. That's the problem for the time for the 2D problem. And now we wait and you wait, and it's the time for the 3D problem. Actually, it could be a lot more dramatic. When you read the second time, the time is a little different. For some reason. So it's about 10 times slower, okay, 10 times slower. And if you take a problem like this, a 3D problem, and run it on with a very large grid, then you'll see huge. This gap will increase in quite a bit because you have this memory effect. You have a lot of things going on. So it is. 3D problems are very hard to solve with direct methods. That's why we need iterative methods, okay? So having said that, now I'll continue with one-dimensional projection methods. I've talked about steepest descent. Now we're going to talk the MR, minimal residual algorithm. So this one takes as a subspace the span of the current direction R, residual R, and it projects onto AR. So the L is AR in here. So from what we know from the theory, we know that we're minimizing the residual because L is A times K. And so here is the algorithm: compute the residual, compute alpha in this way by imposing the fact that the new residual has to be orthogonal to the old one, and then update X. So that's very simple. And you can use the same trick to have one matrix vector product instead of two. Okay. So now we can show results, convergence results. You have to make the assumption that A is positive definite, meaning that A plus A transpose is symmetric positive definite. With that, you can show global convergence. You have some bounds like this. And then this is very simple proof here, similar to the one with the conjugate gradient. That's kind of straightforward, actually, in this case. Okay. The third method, the third projection method, is where you take D in the form A transpose R. So now your search direction is A transpose R. And you're doing the same thing with minimizing the residual. So you take L to be A times K. So E is AD, A times this. And you get the algorithm here. I'm going to skip this the whole thing, because it turns out that this is equivalent to solving the normal equations with steepest descent. So all these three algorithms are actually interesting because they reflect what you see also in the literature about iterative methods. You have the CG, or conjugate gradient type methods, you have MR, and you have GMRAS, you have all these methods around minimizing the residual, and then you have all these methods around solving the normal equations. So these are the three types of methods you'll see. And this is typically not very effective. Solving normal equations is not very effective. Okay, so next I will start now with Krylov subspace methods. And for the motivation, I'll just start with the one-dimensional projection methods. They are all of this type. Okay, so and alpha is defined to optimize a certain function, but it's all local. So you do things locally. In other words, you don't care about what happened in the previous iterations. Okay. So in MR, for example, you write x of alpha, which is this, x plus alpha d, and you minimize this norm, the residual norm, with respect to alpha, and you get the new iterate. Now, this is equivalent to imposing orthogonality. Now, the search direction tends to go like this, down, and then to the right, and then so there's zigzagging towards the solution. Here, what we're showing here is the ellipsoid that corresponds to the A norm. So it's the equipotentials, if you like, or the function of that has to do with the error, the norm of the error. And the center of the ellipsoid is a solution. So you're going to the solution by zigzagging like this. So the question you ask is, can we do better by combining iterates? So essentially, this one-dimensional type methods are oblivious to what happened in the previous iterations. They're short-sighted, essentially. And you'd like to get something that's a little more efficient by combining these previous iterates. And that's what you get with by looking at these Krylov subspace methods. So one observation here, which is important, is the link with polynomials. So if you consider the k plus first residual, you'll find that it's of this form, alpha I minus alpha k rk, all right? It comes right from the definition of the algorithms. And then this rk is itself is a combination, could be written the same way, recursively, and you can end up with a formula like this, all right? So this here is essentially a polynomial. I'm going to try to do a little better job here. Okay. It's a polynomial of A times R0, and that polynomial has a value of 1 at 0, so it's of this form. So then you can show that xk plus 1 is x0 plus a polynomial of A times R0, and this polynomial here, Q, is exactly this one. Okay, that's not very hard to show. So that brings us to Krylov subspace methods, because this is one particular polynomial that we used, and it's basically, each of these is only based on the previous iterates. And you can ask the question, can I get a set of alpha k's, set of alpha i's, that minimize the norm of this over something that looks like this, right? So that is what leads you to Krylov subspace methods. Now, to define them, you need to define first the Krylov subspace. So Krylov subspace is something of this form. So essentially it's a set of polynomials of A times V1. And there's some very simple properties here. So this is the set of polynomials of A times V. They have there's some sort of invariance after what is called the minimum polynomial from mu is reached, etc. So these are really simple considerations. Now we go to the first algorithm we will see, and that is the Arnoldi method, the Arnoldi's algorithm. I just realized that I forgot to show you one experiment with the MATLAB. That's to do with the one-dimensional type method. So let's go back to that now before I continue with this. So I'm sorry, let's go here. Okay, so here I have to go demo 1D projection methods. Oh. Oops. All right, here we go. So these are I got 4 methods going on here. I'm comparing also with Gauss-Seidel. So here is what you see from these different methods. I'm going to try to see this thing. Oh, that's the problem with that. There we go. Make it bigger. All right. So you see steepest descent is somewhere here, the black one, and then you have mid-res, which is this one. This one is actually Gauss-Seidel, which is faster in this case. And this one here is normal equations. Okay. So yeah, that's all. I'll come back to this in a second. Then one more thing that I haven't discussed too much here so far is the idea of preconditioning. So this one will show you an experiment where you actually add preconditioning. So this is min-res Gauss-Seidel by itself, and then you see what you can get as an improvement if you add preconditioning. This is Gauss-Seidel preconditioning. So you use just the essentially sort of an approximately factorization you get from the Gauss-Seidel algorithm. Tremendous gain. So I don't talk too much about preconditioning in this tutorial because it's a whole different thing, and it would take us forever. So I prefer just to give you a vague idea that essentially it's modifying the linear system by solving it approximately, and the resulting iteration will be a lot faster. So I'm going back here. Go back now to Arnoldi. So this is Arnoldi is simply a method to get an orthogonal basis for the Krylov subspace. It's essentially nothing more than Gram-Schmidt, in which the most recent vector is of the form A times Vj. So you have built your basis up to Vj, okay, and now to get the next vector of the basis, you multiply Vj by A, and then you orthogonalize it. This is just Gram-Schmidt against all the previous VIs, right? And in the process, you get an orthogonal basis, obviously, by construction, but you also have this relation here, which comes from, it's not very complicated to see that, but it comes from the fact that AVJ here is combination of Vj plus 1 and the other VIs. So, and it turns out that this relation that can be expressed really in a very nice simple form. You have AVM, which is Vm plus 1. So we have add one more vector times this vector, this matrix, which is m plus 1 by m, where you see it's Hessenberg, but it has m plus 1 rows. Okay, so that's something. This is something you can exploit in the algorithms. Okay. So if you look at trying to solve linear system of equations, then you can write the orthogonality condition. Now you take the basis you would take here. Now we take V1 to be simply R0, right? R0 divided by its norm, because V1 is supposed to be of norm 1 here. If you take that and you build the subspace from the Arnoldi, then Arnoldi algorithm, then you'll find that the solution is of this form. So xm is x0 plus a combination of the vectors in Vm, and that combination is given by this, what we called ym earlier. Okay, so that's what you have. It's a very simple algorithm. Okay, this is called simply the FOM, Arnoldi method for solving linear systems. Okay, And then you have methods. Now, this method that I just described here uses, this tends to be on the way. Okay, so, oops. I have to see what, okay, good enough. Yeah, so this is when using Lm is equal to Km, right? So then the other methods use Lm equal to AKM. So we're now minimizing the residual, and you use this relation here that I talked about. You minimize the residual, therefore you minimize this. Then you can easily see the solution that you get from here, and this gives you essentially this approach. So xm x0 plus vm times ym, these are linear combinations of the previous VIs, and you minimize this to get the ym. And this is GMRes, and they have other methods are mathematically equivalent. Okay. So let's talk about the symmetric case now. This is going to be a little faster. In the symmetric case, you have the relation. So this matrix HM that you have here, which is VM transpose AVM, this is that Hessenberg matrix except the last row that I've talked about earlier, except the last row. So that matrix turns out to be symmetric. So because the A is symmetric, this matrix is symmetric. If you look at the transpose of this, you've got the same thing. So therefore, in the Arnold algorithm, you only need to orthogonalize against two vectors. You don't need to orthogonalize. It's really, the Hessenberg matrix becomes tridiagonal, right? So you only need to orthogonalize against two vectors. That huge savings, this is at least in theory, obviously. In practice, you have other difficulties. You need to do some, well, it's not going to be orthogonal after a while. So this is what you get for HM is tridiagonal. And then you get the Longshaw's algorithm. That's how you get the Longshaw's algorithm. So they have, in the Longshaw's algorithm, you have this three-term recurrence that comes from the fact that HM is tridiagonal. So Vj plus 1 is AVJ minus alpha Jj minus beta J Vj minus 1. And these are all computable from this inner. This is only one inner product, and this was the previous one. And so this is a very, very simple and nice three-term recursion. But in practice, you don't get orthogonality. You lose orthogonality very quickly. Okay. So the Longshaw's algorithm is written here. As you see, you have you compute this first. It's a form of modifying Bramford. It's implemented in that form in the sense that you compute this first, and you compute this inner product, and then you subtract in here, and then you normalize. Okay. So then now this is something that would take a little while to describe in detail, but you can ask the question: how do I implement a linear system solution with a Longshaw's algorithm? So I could use FOM, right? So at some point you need to solve a tridiagonal system, and you have a combination of the previous VIs, right? You add that to your solution, the current solution. That is one way, but it's not necessarily a good way because you need to keep all the VIs around. That's not very practical. So you need to get an implementation that's progressive, meaning that you can get from XM to XM plus 1 by only combining a few vectors. And this is a little bit of a long story that I'm summarizing here. You could do one first version is to orthogonalize, use the tridiagonal nature of HM to come up with a solution which we call direct IOM. So direct sort of incomplete FOM, if you like. That's one way, that's one possible solution. And the other solution is to just derive properties that you have, that you know from this algorithm, the Longshaw's algorithm for linear systems, to see that you can actually write it differently. And that's all coming from these properties. And you come up with this algorithm here, which is the conjugate gradient. Okay. That it wasn't discovered this way. I have to be very clear about this. The way it was discovered was from different angles. People were looking at geometry, saying, well, gradients tend to go this way. You remember this picture of the gradients that are orthogonal to each other? They say, let's draw a line, parallel tangents or something like that. So it's really, you know, when you, in the old days, they used to teach us geometry, conics and ellipsoids, and so that comes exactly from there. So they do a direction that would directly from one point to the center of the ellipse, or ellipsoid. So that's one consideration. But there are other ones, other ways of deriving this. Okay, so now let's see here. I thought I had, yes, I got Krylov, Demo Krylov. Let's look at that. So here are a number of methods. One of them I didn't talk about in this discussion here. So here is FOM, which is in black here. This is for a system, linear system obtained from, I didn't want to show you the script itself, but it's a linear system which you obtain from a Laplacian, which you shift slightly to make it indefinite. And you have, it's an advection diffusion problem. So you have actually advection terms that makes it also not symmetric. It's not a very large problem. So, but you see here is GEMRAS below it, the FOM, and then what you see here is another method which I haven't had the time to describe, and that's the BiCG. Okay, BiCG is a method that uses A and A transpose. Uses a Krylov subspace with A for the search space, the Krylov subspace of A transpose for the constraints, and you get something like this. Okay. See if there are any questions so far. All right. Questions here? Yes, that's actually a good question. Why do we have all these wiggles? That's because the problem is somewhat indefinite, you know, and then you have in the BiCG you have these the scalars that are defined that we divide by an inner product that is not guaranteed to be positive. It could be actually zero. It could actually be zero. So it, you know, you're in the case where the problem is indefinite, it could be, so that's what happens. You go into these zones, but the miracle is that it still works. And that's really the thing that amazes me. It still works in spite of the fact that theoretically there are not that many strong foundations for it, because you have indefinite products. Everything is really not quite rigorous. Yeah.
We have observed that if one uses the three-term recurrence, then algorithm is somehow less stable, although informally compared to when one includes all the vectors, which should basically span the same space. So you have an explanation for that?
The analysis of the Longshaw's algorithm has been done a while ago, and there was a lot of work to explain how this the algorithm becomes unstable. It actually becomes unstable as soon as one eigenvector converges, and so what you could do to correct the problem is to reorthogonalize. So you lose orthogonality completely, but you reorthogonalize and things work pretty well. In most of the things we do these days, we just reorthogonalize. So you lose the benefit of the three-term recurrence, actually. Other issues or questions? So I think this is just actually I'd like to give the historical perspective about this stuff, because it's really, really interesting to see what this is from those days when it was invented. So the method itself was discovered independently by two groups, one in Zurich and one in the US, and that team was UCLA. And the person in Zurich is Hessner Stiefel, and in the US here was, sorry, Hessner Stiefel, whatever. And in the US is Hestinus, okay? Edward Stiefel, and I forgot the first name of Hestinus, I should remember it. So anyway, and they were working completely independently, and when there was a meeting one day in Los Angeles, and they were comparing notes, and they discovered that it were exactly the same method that they were talking about. So they decided to write the paper together, and this is what this is about. The person you see here, Marvin Stein, was actually a faculty member in our department in Minnesota. He was from Minnesota, and Hessinus also is from Minnesota, actually, originally. Good Minnesota. Okay. So, eigenvalue problems now. So these are all the possible applications. You can see again stuff I mentioned earlier. Eigenvalue problems in quantum chemistry use the biggest portion of the time used by supercomputer centers these days. So you're also talking about applications now in data analytics. We have very often here, we actually are interested in the SVD. Sometimes the eigenvalue problems with the context of the Laplacians and things like that. We'll see that in the tutorial later. So the eigenvalue problem, you have the various types. There's the standard one, generalized eigenvalue problem. We have a quadratic and nonlinear. In terms of a nonlinear eigenvalue problem, what is common is essentially to see something like this, where f here is a certain function which is nonlinear. Of course, the simplest one is when you have a polynomial term, but they could be more complicated than that. But there is also what I call a nonlinear eigenvector problem. So the nonlinear eigenvalue problem is like this, right? A of lambda x is equal to 0. Lambda is what you're looking for, and x is the eigenvector. But for the kind of problems you see in quantum mechanics, that tend to be like this rather. So it's a plus lambda b plus a certain function of the eigenvectors times u equals to 0. And these are the eigenvectors that are involved in the computation. So for example, in the Kohn-Shamick version is exactly like this. So these are what is called the occupied states, what are called the occupied states. So this function could be complicated function that involves the eigenvectors. You can to get this function here, you actually need to solve a Poisson equation. There's a lot of things that go in here. It's very complicated. Okay. So, right. Okay. Now let's go to some of the tools that are used. The projection process. I'm going to discuss this in detail in a second. So these are the main tools that are used when that you will find in any code that computes eigenvalues. The first one is projection process. I will discuss that in detail. Then the second one is shift and invert. To focus on a certain eigenvalue, you select a shift sigma, and then instead of working with A, you work with this matrix A minus sigma inverse that tends to enhance the eigenvalues around sigma. That's what you sometimes makes it very effective because that's what you're looking for. For example, the simplest one is the inverse power method. Okay. So in this case, what you do is factor this matrix once, and then you iterate with it. The next tool that's used is deflation. Okay. So when you have computed an eigenvalue, these are deflation and restarting. There's a whole class of methods that revolve around these ideas of deflation or implicit restarts or restarting. So you have complete eigenvalues, and now you don't want them to appear in the calculation, so you remove them from the picture by using deflation. Okay, so restarting essentially consists of combining this with the sort of information you get from the previous iterations. So all packages that you will encounter will combine one way or another these tools that I just briefly discussed here. So these are some of the available software packages you will find these days. IRPAC is an older one now. It's actually often used as a benchmark because it's kind of fairly well known, has been around for a while. But you have things like Feast, use filtering, you have Prime, you have our code here, EVSL. There's a lot of these codes in here. They're all, these that are listed here focus on computing eigenvalues on one end of the spectrum. Okay, so it's left or right. There's also interest in computing eigenvalues inside the spectrum, well inside the spectrum. So we call this an interior eigenvalue problem. So this is shoot and invert and so on. So let's talk about projection methods for eigenvalue problems. So the same thing as for linear systems, you're giving two subspaces, and now the condition you write is exactly like this. So you're looking for lambda tilde, the approximate eigenvalue, and u tilde, the approximate eigenvector, such that you have this constraint here. So this is the residual. So it's a minus lambda tilde u tilde, right? That has to be orthogonal to the subspace L. Okay, and then again, you have these two types of methods. I'm going to talk mostly about these types of methods. So let's talk about what is called the Rayleigh-Ritz projection. It's a very common thing you will find. It's a basic tool that's used in eigenvalue calculations and in other, not necessarily packages, but in calculations dealing with eigenvalue problems. So you have a subspace X that you know contains a good approximation to your eigenvalues or eigenvectors. Then the question is, how do you extract eigenvectors from it? And then the answer is just Rayleigh-Ritz, which is nothing but a projection method with k equals L equals the span of Q. That's all. So you come up with a problem like this. So that's the Rayleigh-Ritz process consists of solving this eigenvalue problem here, where Q is the basis of that subspace X that you have here. That comes directly from imposing these conditions. It's a very simple technique. For example, I can give you one example where this could be useful. Suppose you're using the power method. If you know the power method, if you use the power method, and it turns out that the dominant eigenvector, the one that gives the largest eigenvalue in modulus, that if that's complex, which is very common if you have an asymmetric matrix, right? The dominant eigenvalue could be complex. Then the power method won't converge because you have two. It would oscillate somehow. But if you use a projection with only two vectors, two real vectors, right? The two consecutive ones. You do a Rayleigh-Ritz with two consecutive vectors, then you get the solution right away. It's really very simple mechanism to resolve that issue. Okay, so this is just describing the procedure in detail, and then there's some property here which I want to skip. Now, one of the best known methods in eigenvalue calculation is subspace iteration. Subspace iteration is essentially just a Rayleigh-Ritz with a subspace of this type, that's all. Or more generally, instead of a to the power kx, you could p of a times, pk of a times x, but pk is a polynomial. That's another, it's more general. It's a very simple procedure. And that is described here, okay? Now, there are some theoretical results that show the convergence. If you recall, the convergence result for the power method, it's simply lambda 1 divided by lambda 2, right? Lambda 2 divided by lambda 1 to the power k, 2k steps, where lambda i's are now labeled decreasingly according to the moduli. So, well, is this method competitive with Krylov type methods? So this is actually an interesting point, because we heard a little bit about randomization algorithms. These are essentially, you can view a randomization algorithm, at least the way they are described in some of the recent literature, as a form of the power method, right? You could do 1 or 2 powers of A, to power of degree 1 or 2, and that gives you enough separation that you could use now projection method. So they tend to be more robust than Krylov subset techniques. They tend to be less sensitive to noise than A. So there are some advantages in using subspace iteration versus Krylov. Krylov is a little more, it's a little more demanding. You cannot change A, you cannot this. It's a little bit difference between the two. So in Krylov subspace methods, then you do simply a projection method on this Krylov subspace, which I already described. We have seen already the Arnoldi procedure. Okay. And now we're looking at the Hessenberg matrix here. This is the last column, last row, which is, this is an m by m plus 1 row. Okay. This is the result of the Arnoldi process. So let's look at what you get from the just applying the orthogonality condition. So you want to write the eigenvectors of it's a combination of the OIs, and you write the orthogonality condition, and you end up with this eigenvalue problem. Okay, so that's an m by m problem where Hm is Hessenberg, and then the eigenvectors are of this type. Okay, now this gives you one eigenvector, so you have to go into the details a little bit to see what you could do to get the other ones. Okay. The first thing you do is realize that this procedure here is not realistic if m goes to infinity. M cannot grow to infinity indefinitely, right? So you have to limit it. So you have to restart. And then the simplest thing you can do is this restart procedure, which you take at any time the current the new starting vector v1 to be the latest eigenvector you had. Okay, and then you could do deflation as well. Deflation is now you add. So the first idea is restarting. You cannot use a subspace of arbitrary large dimensions. So you could take, for example, a dimension of 10, take the latest eigenvector and use that as initial guess to the next Arnoldi process. Then the next thing is, once you have completed one eigenvector, what do? I could just deflate it, and then get the next eigenvector. So this is one of the earliest methods for deflation. And here's an interesting observation here. If you take this matrix, U1 is an eigenvector. Let's say the dominant eigenvector, for example. And we take the matrix A1 equals to A minus sigma U1 VH. VH is actually an arbitrary vector, such that the only requirement is that the inner product of V and U1 is equal to 1. So you scale it so that the inner product is 1. Then the spectrum of this matrix is actually right here. So it's all the eigenvalues are preserved except the first one, which is shifted by sigma. So this is called Widland deflation. It's explicit deflation. You explicitly remove move away the eigenvalue lambda 1 so that you won't appear in if you do the power method or whatever. But you could, so you could use explicit displacement in this form. You could put these in a set of columns, and that's explicit deflation. And that's what you get with in the algorithm here if you modify it. So I'm going to just show you this actually in MATLAB instead of showing it here. So we have a loop here for eigenvalues now. I can compute any of the eigenvalues. And each time, what I do is I use an analogy process where I have deflated the matrix. So I have to have somewhere my AK. It doesn't appear here. Yeah. So anyway, I have to orthogonalize against the previous eigenvector that I have computed. There is another process, another way to do this, which is the idea of locking vectors. So you put your vectors that have converged as the first few vectors in your basis. So these are now orthogonal vectors, and they're what we call sure vectors. If the matrix is not symmetric, this is an orthogonal basis of an invariant subspace. So HM would take this form, okay? And so these are two ways of doing it. I'm going to just talk a little bit about the previous one. In let's see, in the demo that I have here. Eigenvalues here, okay. Okay. So I have just test R with restart. Yeah, okay. So this is a very simple process. I can show you here. So this is that. Remember that matrix we called the Markov chain matrix. That's the one. So that it's a small matrix. Okay. Let's just show the algorithm first. R.M. Okay. This is the algorithm that does Arnoldi with restarts. So as you can see, I'm going to show you very quickly what it does. This is it has an outer loop, and then it has an Arnoldi loop, which is right here. And this outer loop is just the restart. So initial vector is the eigenvector you had from the previous iteration, which is set at the end, set right here. This is the eigenvector, which you use for the next iteration. And the rest that you see here is simply an Arnoldi loop. It's exactly what you see here. It's, you can multiply by AV, and then you just no, sorry, I'm talking about here. Working at the wrong line. This is just the standard Gram-Schmidt, modified Gram-Schmidt. Arnoldi, okay? So, and then you can see here that it's essentially just going down, very simple. Let's look now at the same thing that I add deflation. So this computes one eigenvector at a time. You just tell it the largest or the smallest one. It's a little basic. So what I will do is, this is a little more, all right, a little more challenging. RD, there we go. So here I add deflation. So now in my call, I have the number of eigenvalues I want, the order, which is large or small. It's exactly like your order sequence of entries, ascend or descend. And then I return a set of eigenvectors, the sure vectors, and the upper triangular form associated with that. So let's try that. So here now I'm going to do and test or restart and deflate. Okay, this one is a matrix mark or 30. So this is the triangular march. Remember the random walk on a triangular grid. And I'm asking for 4 eigenvectors, and let's try it. Test arm or near. Right, there you go. So these numbers that you see are NaN. I put those in on purpose. So let's get rid of this one here. Let's try it again. Close all. because I have 4 curves, right? And okay, here we go. Whoops. Is running the wrong one? How come? Okay. Did I do the right thing? No, there's something wrong here. I just had a yeah. 4 maybe is equal to 4. Something went wrong with my script somehow. Yeah. It's probably didn't, at least if I say hold on, it's probably skipped that thing. I don't know what happened here. I have to look at it later. Something went wrong with my script here. Let's switch quickly here. RD. What you should normally see is 4 different curves, one for each eigenvalue. Okay, there we go. And when I get in here R, yes, R is computed correctly. But the eigenvalues are not shown correctly for some reason. Sorry, the error. Yeah, I think I had something strange with the. Let's just go one more. Give me a second. Now it's clear. Have it clear everything. Yeah. So, oh, error is not recognized. That's what it is. Okay, so this happened here. Test RD. Yeah. No. Give me a second. Test RD. Okay. So res. Okay. So you see, I was still working on this stuff not long ago. Now it should be the right thing here. Someone pointed out the right error. So now we should do the close and do it again. Yeah. You see the eigenvalues that are computed. This is given as one curve. I had to put in, in MATLAB, you can separate this curve by putting nans in between. Now they have one for each eigenvalue, one curve for each eigenvalue. This converges, and then this takes it from, from this as initial guess here. You get the next eigenvalue that was computed before. Okay, so you can do this and compute as many eigenvalues as necessary. All right, so let's see. Wow. Okay. So the next thing is the Long-Shor's algorithm. And here I'll show you something that it has to do with the way this can converge. So here is the algorithm that you get in the method you get from Long-Shor's gives you a tridiagonal matrix. Now you compute the eigenvalues of this tridiagonal matrix, and they should converge to the eigenvalues of the original matrix. And it turns out that the convergence theory will show you that you're converging from inside out. So the first eigenvalues that you converge to are the ones at the extremities of the spectrum. So these eigenvalues now are real. And then you will see how it works. You can show that the eigenvalues converge. You converge first with the first eigenvalue, and then the second one. Then you go all the way inside. Here's a very simple. I will just close everything first. Right. So here's what this curve shows. It's a curve you will often see in the literature that to illustrate the convergence of Long-Shor's. Each of these horizontal lines is an eigenvalue. All right. So this is a small problem. I don't know what size it is. It's a very small problem, and So we could do a projection here, and every 5 steps or something like that, I show the eigenvalues. And you can see they start to converge here. It's not quite, you don't have any convergence. And then all of a sudden you start converging here. And you get 2 eigenvalues that are close on both ends, here and here. And then you have a few more. This is getting close, and this is converging. After a while, the both ends would have converged completely. And then you go inside, and it takes all the way. You will have to wait all the way to the end to get all of them converged. So it converges from inside out. Now that's a phenomenon you can easily understand from theory, essentially. Okay, so this is the Long-Shor's algorithm. And then there are all these other, so Long-Shor's, the one that I just showed you would not work at all if I didn't do reorthogonalization. You have to reorthogonize. You normally, in principle, you need the 3-term recurrence would give you an orthogonal sequence in theory, if you had full exact arithmetic. It turns out that as soon as you have one eigenvector that starts to converge, then it's not very difficult to analyze. Then you start losing linear independence. So the vectors of the basis become dependent. It's as if you're introducing more copies of eigenvectors, the first eigenvector, and then the second eigenvector. And so there are a lot of techniques that have been developed to use that information to correct the process. So this is selective orthogonalization. We orthogonize against these eigenvectors that have already been computed, because we know that those were the ones that cause problems, because the vectors tend to reappear in those directions. There are also a technique called partial reorthogonalization, where you only do reorthogonalization when you need it. At the beginning, there's no need for reorthogonalization. So there's all these different techniques that have been developed. But really, when it comes down to these implementations, I would just use full reorthogonalization. Don't have to worry too much about it, because you gain very little with partial reorthogonalization. You start losing independence at some point, but that point is quite early very often. So you don't have to try to figure out how to save a little bit of time. So that kind of, these are the things that you need to know about reorthogonalization. So a lot of the things that you do, especially if you have a subspace that's not too big, then you might as well just use full reorthogonalization. See if there are any questions. No? Okay. Any questions so far? Okay. So I'm getting actually to the end here. I have about 7 minutes left. So this is what I was talking about in for the test for the convergence. You see these eigenvalues here, lambda1 is approached by lambda1 tilde from the right side very quickly, and then this one is like that, and so on, and you have convergence from out to inside out. These are some of the results that show these convergence results. Now I'm going to talk very briefly about the biorthogonalization methods, where you have for the non-symmetric case. So this process of the Long-Shor's algorithm has been generalized to the non-symmetric case by using both A and A transpose. So you have, this is, if you look at only this part here, this part, it's exactly like Long-Shor's, you see? There's no difference in the way this is written with respect to the standard symmetric Long-Shor's. But the only difference is that the alphas and betas that you see here are obtained by using this sequence, the W's. And the W's involve A transpose, or AH in the complex symmetric, the complex non-symmetric case. Okay, so these are only necessary because you need to compute these alphas and betas. So you get a tridiagonal matrix, but again, this was related to the question that was asked earlier. You see here you have this division by delta, all right? This delta here look at this. It's a linear product of these two things, and that could be very well be a zero, or it could be small, or it could be, we don't really know much about it. So we should expect to see oscillations, just like for the BiCG. And that makes it really a very difficult algorithm to use in practice. So, but people have used this in some situations. Okay, so that's essentially all I had to say about these Long-Short reduction type methods. Now, the next thing, as I will start, I think tomorrow, I'll probably just stop here and see if there are any questions. We have about 5 minutes for questions. And then tomorrow we'll start talking about graphs and about, yeah, so essentially, this is just a really brief background on graphs. And then we'll talk about some other things that have to do with models for sparse matrices and so on. Okay. So discussion on eigenvalue problems. Any questions? Any things with the? So let's see if I have missed any demos first to finish up with this. Go ahead. Yeah, sorry. Yeah.
It's just the correct pronunciation of the name Lanzos. The CSD is pronounced like tsunami or tsetse-fly, and the final S is pronounced like SH.
Lanzos. I heard that before, yes. But everybody says Lanzos. Yeah. It's Lanzos. Okay.
People say Schrödinger.
Schrödinger.
In the US, you know.
Okay.
So I'm not surprised at that.
Yeah. Yes, I have also some other demos here, but I would probably, you know, with shift and invert Arnoldi, and I didn't show you the Long-Short algorithm. Just look at that Long-Short. I should Lanzos. Okay, it's difficult here. You see, I just very briefly show you the loop here. So here is that first statement, AV minus beta times V old, and then you compute alpha, and then this is just to store this thing in a matrix. I'm storing it as in a full matrix, and then you see you have your you subtract alpha V, your reorthogonize. You see, this is exactly reorthogonization, and then you compute the norm and you scale and you store this in the matrix and you're done. This is the whole thing. It just takes a few lines. Okay. Yeah, question. There was a question. Jim had.
Yeah, so you know, the idea of reorthogonalization, I think, is important for eigenvalue problems, but not necessarily for solving a linear system. Right?
Yeah, right. Yeah. So that's right. Yeah. So you made a good point. I didn't mention that earlier. So yes, for solving eigenvalue, for solving linear systems, it may not be necessary to reorthogonalize because you still get really decent convergence. For eigenvalue problems, you lose everything. You know, it's really you did garbage in the end. For linear systems, you still get reasonable answers. Yeah. I cannot hear you very well. Sorry about that.
In terms of the future of the computing, I mean, eigenvalue solvers and linear system solvers
are
essential, and we're at the stage that distributed computing is kind of not really aligned with the classical projection type methods and so on. So, how do we proceed from here? I mean, how think we should proceed?
Yeah, so the question is what's the future in terms of eigenvalue problems versus linear systems versus, eigenvalue problems will always be important, guaranteed. And also, I think they're coming in a different form, in the form of the SVD, you know, so that's another very important part of what is going on in data, you know. So, but as far as linear systems, I think, I wouldn't say we've solved, there's been an enormous amount of work done on direct solvers. And I think it's settled now, more or less. You have still work on parallel direct solvers, but really there's still work to be done on iterative methods a little bit. But that also is kind of not as, let's say, not as urgent as it used to be. But I think because of the different exchange of directions, I think eigenvalue problems or SVD type calculations will become definitely more important. Another question, or let's see if there are any things in here. There's a chat. So there's a comment here. I think everything you showed applies to both sparse and dense. Are these algos which work better for sparse? Yes, a good point. Anything to keep in mind, or anything special to keep in mind when dealing with finding eigenvalues of sparse matrices? Yeah, if you had often when you have dense problems, you really often you will complete all the eigenvalues, and the types of algorithms there are different, So, but these are really meant for a small number of eigenvalues. That's what makes it so. And I think algorithms work better for sparse. All of this, these things I described work, of course, better for sparse cases. The matrix vector product is order n squared for the dense case. And if you do a lot of those, then it becomes expensive. See if there are any other things in here. Yeah.